Hello everyone, welcome to Brain Blitz Audios. Today in this episode of NEET Preparation, we'll be looking at previous year questions of physics in medical entrance examinations in India. Today we're dealing with the chapter Magnetism and Matter, which is an important chapter. This is the fifth chapter of the grade 12 syllabus for physics in CBSE. Now don't forget, just stick around, we'll have an extra question for you in this episode, so stay tuned until the last minute of the video. Let's look at our first question. Curie temperature is the temperature above which a ferromagnetic material becomes paramagnetic, a paramagnetic material becomes diamagnetic, a ferromagnetic material becomes diamagnetic, a paramagnetic material becomes ferromagnetic. So, what is the Curie temperature? If we look at a graph for magnetic susceptibility versus magnetic permeability for a ferromagnetic material, we find that above a certain temperature, it becomes paramagnetic. So therefore, option A will be the right option. If we look at options B and C, it says paramagnetic becomes diamagnetic, ferromagnetic becomes diamagnetic. Both of these cases are incorrect. Options B and C are incorrect. And option D states that a paramagnetic material becomes ferromagnetic. This may be true, but again, in this situation, the temperature has to decrease. And in the question, it says Curie temperature is the temperature above which. So this implies an increase in temperature. So therefore, option D will also be incorrect. Another fact is that all paramagnetic materials might not be ferromagnetic, but all ferromagnetic materials can be made paramagnetic due to the instability of the domains caused by heating. So therefore, option A is the right option. Next question. Of the following figures, the lines of magnetic induction due to a magnet south to north are given by, and we have our four options, 1, 2, 3, 4. So what are the conditions for magnetic induction due to a magnet? Number 1, outside a magnet, the magnetic field travels from north to south, and inside a magnet, the direction is south to north. If we look at our figure 4, we see that inside the magnet, it's flowing from north to south, and outside the magnet, it's flowing from south to north. Now, this is basically the inverse of the conditions given. So option D is incorrect. Now, what about option C? I mean, the third magnet here shows that the magnetic field lines inside the magnet moves from north, south to north. At least the straight lines do. However, if you look at the curved lines, it says a different story. It says that the magnetic field moves from north to south. So this part of the magnet is contradicting our condition that inside a magnet, it moves from south to north. Inside a magnet, the magnetic field moves from south to north. The straight lines follow it, but not the half circles. So option C is incorrect. What about option B? In option B, let's look. The magnetic field lines inside a magnet move from north to south, and over here in one part of the magnet, in the outside, it moves from south, the magnetic field moves from south to north, while in the other end, it is a different story. The directions are reversed. This condition cannot be possible. It is outside a magnet one direction, inside a magnet another direction. Directions cannot interchange. So therefore, option B is also incorrect. The right answer is option A, which is our first magnet. See that in our first magnet, magnetic fields inside move from south to north. Again, if you look at the half circle, south to north. And outside, it moves from north to south, as we are accustomed to, which is why option A is the right option. Magnet 1 represents the correct direction for lines of magnetic induction due to a magnet. Next question. Materials suitable for making electromagnets should have A, high retentivity and low coercivity, B, low retentivity and low coercivity, C, high retentivity and low coercivity, D, low retentivity and high coercivity. Now look at our question. Here it's saying that the material suitable for making electromagnets. For making electromagnets, you should have two conditions. First of all, the material, it should be easily magnetized. So therefore, it should have a low coercivity. Next, you know that in an electromagnet, we use AC current. And therefore, one of the properties of AC current is that the current changes its direction. This we'll learn in the 7th chapter, but again, electromagnets, they're powered on AC current, so therefore we should have materials made in the electromagnet that can easily change direction. Now, for easily changing direction, there should be a constant cycle of magnetization and demagnetization. Which means that the material must easily demagnetize as well. It should get easily magnetized, and it should also get easily demagnetized. And for getting easily demagnetized, it should have low retentivity of the magnetic field. So the first condition was low coercivity. Low coercivity, again, is found in options A and B, so options C and D get incorrect because they have the condition of high coercivity. And then for the constant cycle of magnetization and demagnetization caused by the AC current, we should have low retentivity. So if we look at our remaining options, option A says that materials would have high retentivity for making electromagnets, which is incorrect. The right answer is option B, low retentivity and low coercivity. Easily magnetized, low coercivity, easily change direction, which means they have a constant cycle for magnetization and demagnetization. In order to make this constant cycle, the material must be easily demagnetized as well. So easily demagnetized means the material has low retentivity. So both low coercivity and low retentivity makes the material suitable for making an electromagnet. Option B is the right option. Next question. Magnetic lines of force due to a bar magnet do not intersect because a point always has a single net magnetic field, the lines have similar charges and so repel each other, the lines always diverge from a single force, the lines need magnetic lenses to be made to interest. Now, we've all known that like poles repel and unlike poles attract. And we also know that magnetic lines of force do not intersect in our earlier classes. But why does this happen? Imagine that you have a magnetic line of force. These are curves. So you know that at a point, the tangent in that direction, the tangent of the magnetic field line gives you the direction at that point. So if we have a hypothetical situation where both magnetic field lines intersect at a point, so as you can see, you have one direction caused by this tangent and another direction caused by that tangent, because at the point of intersection, you'll have two tangents. Two tangents means two possible directions. And we have also learned that two possible directions is a scenario which does not occur. So that's why magnetic field lines of force do not intersect. So that means one point of a magnet will always have a single net magnetic field. It is due to this property that there is this unique phenomenon where magnetic field lines of force do not intersect. Lines always diverge from a single force is incorrect, because in the South Pole, they converge, and the lines of similar charges and so repel each other. We're talking about magnetic lines and not electric. And the lines need magnetic lenses to be made of interest, which is also incorrect. The right answer is option A. Magnetic field lines of force due to a paramagnet do not intersect, because a point in a paramagnetic field line only has a single net magnetic field. This is due to the fact that there is only one tangent which can occur in a magnetic field. If we have two tangents, then there'll be two directions, which is not possible. And that's why magnetic field lines of force do not intersect. Next question. At a temperature of 30 degrees Celsius, the susceptibility of a ferromagnetic material is found to be Xi. The symbol for magnetic susceptibility is Xi. Its susceptibility at, say, another temperature that is 333 degrees Kelvin is, Celsius is. So, first things first, convert both temperatures into Kelvin. So that is 273 plus 30. That gives you 303. And then we have 273 plus 333 degrees, which gives you a total of 606 degrees Kelvin. Next, in this question, we use the Curie's law. In the Curie's law, it states that the magnetic susceptibility of a material is equal to mu naught C divided by T. Now for a material, C and mu naught are constant. So therefore, the magnetic susceptibility is inversely proportional to the temperature. And that is the important relation that we'll be using here. Now, since magnetic susceptibility of a material is inversely proportional to its temperature, magnetic susceptibility at the first case divided by magnetic susceptibility at the second case will be equal to temperature in the second case divided by temperature of the first case. Temperature in the second case is 606 divided by temperature of the first case is 303. 606 by 303 on dividing gives you 2. So the ratio is magnetic susceptibility of 1 divided by magnetic susceptibility of 2 is equal to 2. So over here, we'll write it as magnetic susceptibility of 2 divided by magnetic susceptibility of 1 will be equal to 1 by 2. This is just the inverse of what we just wrote. And therefore, we can write that magnetic susceptibility of 2 will be equal to magnetic susceptibility of 1 times half. Susceptibility of 1 is just Xi, times 1 by 2 can be written as 0.5. So 0.5 Xi. And which of these options have 0.5 Xi? Option 2. So option B is the right option. Option A is the magnetic susceptibility at 30 degrees Celsius. And 2 Xi does not occur. For that to occur, we should use the relation that Xi1 is equal to 2 times of Xi2. But here we need to find out the value of Xi2. So incorrect. And 11.1 Xi is not found in our calculations. We use the calculation by using the Curie's law. Xi(m) is proportional to temperature. Magnetic susceptibility of a material is inversely proportional to its temperature. And we converted the temperatures given to Kelvin and used Xi as a common variable for susceptibility in the first case, and using that we found out our answer, which is 0.5 times xi. So at 333 degrees Celsius, the magnetic susceptibility of a material gets halved from its susceptibility at 30 degrees Celsius. Option B is the right option. Now let's look at this question. 2 points, A and B, are situated at a distance x and 2x respectively from the nearer pole of a magnet. The length of the magnet is given as 2 centimeters. The ratio of the magnetic field at A and B. So let's draw the diagram first. We have a small magnet, and this magnet is 2 centimeters long. Then towards a point A, the length is x. Towards a point B, the length is 2x. And so therefore, this is the scenario that we get. We need to find the ratio of magnetic field at A and B. So if you look at this position, both the points A and the points B lie axially to our given bar magnet. So what we'll do, we use magnetic field at axial position. And what is our formula? B is equal to mu naught by 4 pi times 2m divided by r cubed when x and 2x are small. I mean, when the length of the magnet is small compared to x and 2x. So over here, we'll get the relation B is inversely proportional to the cube of r. So B is proportional to 1 by r cubed. So right now, what we'll do, let's get the ratio. B, magnetic field at A divided by magnetic field at B, is equal to the radius at B, the whole cube, divided by the radius of A, the whole cube. That is given as, if you look at here, 2 centimeters is the length of the whole magnet. And the length of the whole magnet is usually given as 2L. So the value of L here is 1 centimeter. And if you're to find the ratio of magnetic field, then that is always found from the center of the magnet. So these distances are counted. Therefore, the radius, or the distance basically, of B will now be 2x plus 1 centimeters, the whole cube, divided by, for the point A, it'll be x plus 1, the whole cube. So now it shortens down to 8x cubed becomes 8x cubed plus 1 plus 6x into 2x plus 1 divided by x cubed plus 1 plus 3x into x plus 1. So now let's approximate it into 8x cubed divided by x cubed. X cubed gets canceled. We have our ratio 8:1, and that is experimentally proven. So we just need to find an approximate value here, and that would give us the right answer. So using our approximation, we got C, 8:1 approximately, as the right answer. And that is due to the fact that B is inversely proportional to r cubed. Now, let's look at our final question. Imagine you roll a sheet of paper into a cylinder, and you're placing a bar magnet near its end as shown in the figure. What can you say about the sign of B dot dA for every area dA on the surface? Now notice that B dot dA is essentially the magnetic flux. So we need to find out the direction of the flux here. So if you look here, you find that the magnetic field goes from north to south. If we have a large enough magnetic field, you find that it enters like this. So therefore, if we were to just draw the cylinder, we find that the magnetic field line enters like this. So it enters into the field. This is for B. And the vector dA for area is now protruding outward. So therefore, now you can see that there is an angle difference between the two vectors, dA and B. Now, if we look at our formula for magnetic flux, we know that over here, the formula is B dot dA, dot product of two vectors, which we can write it as B dA times cos theta. What is the value of theta here? The lines are anti-parallel to each other, so therefore theta will be equal to 180 degrees. So B dA cos 180 degrees. And what is the value of cos 180 degrees? -1. So the value of magnetic flux will be equal to minus B dA. Using this relation, we're able to find out the direction of magnetic flux. Over here, the direction of the magnetic flux is option B, negative. For option A, positive to occur, the sheet of paper must have been kept at the North Pole, so the flux will now penetrate out of the cylinder, and the area vector at the terminal end will also be going out of the vector, so out as a vector, so therefore it would have been positive. But over here, the magnetic field lines, even if you look at this face, even there, the magnetic field lines are getting in, while the vector is actually pointing outwards, the area vector. No sign is incorrect because there is always a sign for flux, and that depends on the orientation with respect to the magnetic field. So option C is incorrect. And option D can be positive or negative. That is disproved by using our equation. Now, in most of the cases, it says that when field is entering into the surface, the flux is negative. Over here, we proved it. Why? Because of the fact that the area vector is pointing outwards while the magnetic field lines are pointing inwards. And that means we have a difference, an angle difference of 180, and using the dot product rule, which is BDA times cos theta, which is cos 180, we found that the magnetic flux will be minus BDA. And that's how we can say that the sign of BDA, B dot dA, is negative. And that concludes this webisode of NEET preparation. Now, we have a lot of videos on NEET preparation, and especially on this chapter, Magnetism and Matter. Don't forget to click the link for the playlist in the description down below for viewing more of our NEET preparation videos. If you want to access more of our useful and interesting content, then don't forget to subscribe to our channel, Brain Blitz Audios. So until the next webisode, take care, stay safe, bye-bye for now.